welcome back to Young Engineers of Today. Today we're going to finish off Ancient Engineering. This one might actually be a pretty short class just because the material we have left is not a whole lot, and the next thing is going to be completely different, so I want to get started on that, with a whole fresh class and everything like that, and it's going to take a minute anyway. But yeah, so we'll get through this in probably a reasonable amount of time. We might end early today. If we do, hey, great, you get some extra time to do whatever you want tonight, or homework, or whatever you end up having to do. If not, and we end up taking the full hour, that's fine too. I mean, it's not going to be a huge deal. I hope everybody's doing all right, though. I hope you had a good couple of days, and I hope you're ready to get started. So on Monday, we talked about basically all of the advances that led up to the catapult. So that was mainly derived from the developments in improving the bow. So, as you remember, bows at first were not able to handle all the stresses on them, so the compound bow was developed, in which you used several different materials to build the bow, which allowed to better withstand the compression and tension forces that the wood on a bow undergoes. Then we started to reach a human limitation, and that is, humans were either not strong enough or large enough to be able to pull heavier or larger bows. And so development at that point went into bows that you actually reloaded with your entire body weight. If you remember the gastrophetes, or the belly bow, and that was the thing that the person leaned against, and it cocked the bow back, and then they were able to put an arrow into it, and there was a trigger mechanism and everything like that. And that was, sort of the next major development, and time went on, and it was more about, increasing the power and size of the bow. At some point, it got to be too large even to be, held. So as bows got larger, then even the gastrophetes, they started needing to be mounted on stands. On top of that, they were generally loaded with winches and things like that. And those got to be sort of miniature ballistas almost. As those got larger, you started running into the issue where the materials they were made out of simply weren't able to, stand up to stresses. It couldn't be further improved upon like a compound bow could, or anything like that. It was just simply too much stress. So they started changing the way that the energy was stored. Remember, they started using torsion energy, basically taking knots of rope and spinning them up so that they were storing the energy instead of the energy being stored in the compression and tension energy of a bow, like the wood. And that changed things for a while. That allowed designs to get, again, larger and larger and fire with greater and greater power. But the problem was they started to become a little bit too complex, and so they needed something simpler. And so that's where the traditional catapult you might think of comes in. Instead of it being stored in a bow-like mechanism with the torsion energy, there was actually just a part at the bottom that stored all of the torsion energy. That was attached to an arm and a bucket. It was lowered with a winch, it was held in place, and then there was a release mechanism which launched it. And that pretty much brings us to the Trebuchet. Well, not quite yet, but in essence, this is the result of further development on the catapult. So yeah, as we know before, catapults can be split into three categories: a traditional catapult, a ballista, and a trebuchet. So a trebuchet launches a projectile from a sling on a pivoting beam. So as you can see here, you've got the sling, you've got something held in it, you've got the whole lever, you've got a counterweight over here. So the first catapults designed by the Greeks and Romans date back to the 4th century BC. As you can see here, this is one of those bows I was talking about. This is I think the Zopyrus's bow, I believe, if I remember correctly. This was what came after the Gastrophetes after it became too large to remain handheld, and they started introducing a winching mechanism in order to load it. But traction trebuchets originated in China and date back to around the same time. So this was actually, I should correct myself, this was developed concurrently with the other types of catapults and separately. So trebuchets were developed by the Chinese. So we'll be focusing on counterweight trebuchets, which were first designed in the 12th century. So 1100 to 1199 AD. So these are descendants of the first Chinese trebuchets, and these siege weapons basically came about from advancements in the Islam and Byzantium civilizations and further development in Western Europe. That being, all in the sort of the Middle Eastern area. So a counterweight rotates the beam through an arc, beam, of course, being the main body of the trebuchet, rotates the beam through an arc that releases the projectile. The counterweight is hoisted into the air and is held in place, usually by a release system attached to the opposite end of the arm. So as you can see, this is a different energy system from a traditional catapult too. Traditional catapults were torsion energy. This is simply just potential energy, gravitational energy, which is not technically a correct term, but potential energy is. There's tons of gravitational potential energy stored in the trebuchet because the counterweight is much heavier than the payload that it's firing. Much, much heavier. So for that reason, you can have a payload be fired over, a very long distance. So as the release system is activated, the counterweight drops, swinging the arm with the sling attached. So not only is it much, much heavier than the actual payload, it swings on a much shorter moment, which means that basically the force is amplified over here. There's greater movement on this end than there is on this end, which increases the speed, and then the movement is increased even more because there's an additional sling on the end, which acts as an additional sort of lever on top of the one that exists here. So as the sling follows its arc, one end is released, and the payload is fired, or released and left to fly. So based on all that, can you guess what might affect trebuchet performance? Just throw some stuff out there, Wind, yeah, definitely, that's one of them. Counterweight, yep, that's definitely another one. The length of the sling, certainly. Yeah, all of these things, yeah, the wind will affect it, obviously, because it will act as a damping force or a helping force for the payload after it's released. The weight of the counterweight will also affect things. The heavier the counterweight, potentially the greater force you can swing your payload with, because you can have a longer arm on the other end, you can have a longer sling, you can have a heavier payload, things like that. The length of the sling will also affect it because that will just be a longer, essentially a longer lever. As long as it's not too long. And the weight of the projectile. So if the projectile is lighter, it will fly further and but potentially have less force. If it's heavier, it won't necessarily fly as far, but it could potentially be more damaging. It's all a balancing act. So yeah, in addition to that, you counterweight mass, the height of the counterweight, so like the length of the arm, the projectile mass, the length of the sling, the launch angle, basically where it lets go, good lord, of the payload, and wheels versus a hinged counterweight, interestingly enough. Well, actually, yeah, why not? Let's spend a moment checking this out. Oh, there we go. Hopefully this still exists. Feel free to spend a couple of minutes messing around with it. We can see how affecting the properties of the trebuchet can affect the distance. Oh, yep, that doesn't need to have sound. So as we can see here, we'll just keep everything the same. We just hit launch, and it doesn't even quite go 100 feet. But what we can do is we can reduce the projectile mass, maybe down to 10, and it goes twice as far, just about. On the other hand, we can change the launch angle and blow up our own trebuchet, or we can have it be, too shallow and it gets fired at the ground. So you can see that generally, you want a launch angle that's as close to 45 degrees as possible on the whole. Oh, okay, so because that offers usually the best compromise between a distance and height. Increasing the counterweight mass is actually sort of a modest improvement to the distance that the trebuchet can fire, but it is pretty easily customizable. Raising the height of the counterweight also makes it fire further. Because the counterweight travels a further distance. But yeah, this is just a simple little thing that sort of gives an idea, gives you a better idea of how these different things might affect how a trebuchet would perform. Oh no, almost in the penalty zone. Very close though. But yeah, so that's pretty basic, but that certainly exists to sort of give a visual idea of how distance can be affected. The distance that a trebuchet can fire can be affected by by these different factors, like the counterweight itself, the projectile, the height the counterweight is at, all those different things. So essentially, a trebuchet is just powered by gravity. So generally speaking, the force that a counterweight applies to a payload is equal to 4 to 6 times of the counterweight arm's length. which is sort of a strange way to put it, but you know, obviously different units are being taken into account here. And the sling acts as a secondary fulcrum, like we were saying before. It's a secondary sort of lever that helps multiply the force a little bit more beyond just the trebuchet itself. So the gravitational potential energy of an object can be found by multiplying the weight of the object against how high it is off the ground. So basically the weight of the object times the height of the object equals the gravitational potential energy. So again, increasing the counterweight or increasing the height of the counterweight off the ground are both good ways to increase the power that the trebuchet can fire an object off. And they're the relation between them is pretty linear. It's not like, you know, increasing the height of the payload is going to be a lot more effective than increasing the weight of the payload or anything like that. So energy stored by the trebuchet is determined by the weight of the counterweight and the height that the counterweight is hoisted. I mean, it's essentially the same thing that was said here, just in a different way. Hoisting it up higher will make the trebuchet stronger. Making it heavier will make the trebuchet stronger. At that point, yeah, it's just a bit of repetition. So now generally its force is equal to 4 to 6 times the counterweight's arm's length. The counterweight arm's length. Blech. So gravitational energy stored by the hoisted counterweight is translated into rotational kinetic energy of the sling on the arm, as well as the arm itself. So the rotational kinetic energy is dependent upon the length of the arm and the weight of the counterweight. So as we increase the weight of the counterweight or we increase the length of the arm, we increase the force that's exerted upon the payload. So this is because of torque or rotation around a fulcrum. See, now instead of turning potential torsion energy or potential torque energy into kinetic energy, we're actually turning potential gravitational energy into torsion or torque and kinetic energy. So torque is one of the results of a trebuchet firing, interestingly. It's a little bit like the opposite, not really like the opposite, but it's a little bit backwards from a regular catapult. So yeah, in this case, the force, in the case of this diagram, the force is the weight of the falling counterweight. So as the counterweight falls, there is a downward force exerted upon it, an upward force exerted upon the other part of the arm, which causes, you know, an upward force to be exerted on the sling, which creates its own sort of torque as it is a secondary fulcrum on the arm, and then the force is multiplied. Just another diagram explaining the same thing. And the sling acts as a secondary fulcrum. We're looking at each of these apart, so, you know, it's there's a bit of repetition here. So the sling releases when a certain angle alpha is reached. And that's generally, you're going to use a lot of Greek letters when you're referring to angles in mathematics. So angle alpha, that's what that fancy A is an alpha. There's, you know, alpha and beta and gamma and delta and so on and so forth. So the sling releases when a certain angle alpha is reached. At this point, the ring connected to the sling slips off and the projectile is launched. So as you can see, there's actually just a ring that's on an additional little pole on the trebuchet. And once it reaches that angle, the force makes the ring just fly off. The sling opens up and the projectile is fired off. And it's really as simple as that. But that only happens because the sling itself is rotating around the arm, just like how the arm is rotating around the fulcrum on the trebuchet. So it is an additional bit of force applied to the payload. But yeah, once it reaches a certain point, the ring is essentially pulled off of the finger, It's a very um, on the nose analogy. The ring is pulled off the finger, and then the sling opens up and the projectile is launched. Yeah, here we get the second fulcrum. So now we can actually see a trebuchet being fired. Not just any trebuchet, but at the time, the world's largest trebuchet. Let me go ahead and link that in there. Turn it up a little bit, so at least I can hear it. But trebuchets are not small machines, as you can see here. Yeah, I agree. As you can see, it's loaded by people walking in giant hamster wheels. And that's how it was probably traditionally done as well. You know, that was one of the best ways to convert human energy into um, gravitational potential energy. Here we go. The lag. Yeah, they go launching a something on fire so it's easier to see. I believe they said it was about 100 kilograms. Well, let me double check that. Oh, 15 kilograms. It's 150 miles an hour. So 15 kilos at 150 miles an hour. So about 30 pounds at 150 miles an hour. The counterweight is about a ton. Oh, the box itself is a ton, and then it's filled with 5 tons of rocks. Let's see here. Let's see it launch the... Well, we're about to see. Yeah. There goes the flaming payload. I really wish they'd followed it with the camera. That would have given a good idea of how far it launched. That doesn't help. Wow. Okay, so it's actually capable of firing something at 1,500 miles an hour. Hmm. They don't actually explicitly say. Let's do some quick, really rudimentary math here. So probably about, let's say, the whole thing is 18 meters. It probably goes up to 20 meters. Let's see, that's how many seconds it stays in the air. An angle of 45 degrees. So let's say half of its speed, 75 miles an hour. On your own computer or through mine? So x is the length of time it stays in the air. Through mine. Well, that's why I put the link in the chat box. 75 minus 9.8 times x. We'll say 0 plus 5 meters. How many meters in a mile? $1,609. So right now what I'm doing is I'm trying to figure out maybe how far it would go. Yeah, my math is wrong. There's no way it stays in the air for 3 hours. I mean, it's impressive, but it's not that impressive. All right, because it's squared. Ugh. I'm not sure I have the mental capacity right now to handle that for some reason. Hold on. 12,700 minus 9.8 x squared 0. 2,700 equals negative 9.8 x squared divided by 9.8. So 1206.32 equals, so let's say that's negative. That's not solvable. It's negative x squared. Let's do that. That's still not solvable. There's clearly something I'm missing here, and it's not occurring to me, and I don't know why. At any rate, if I were to hazard a guess, I would say I could probably launch it a mile or two. At the very most, it's not solvable because I'm doing something wrong. You shouldn't be getting imaginary numbers like mine is because I'm doing something wrong with my mathematics. You can't take the square root of a negative number without imaginary numbers. And it shouldn't be getting to that point, but that's what I'm doing because I'm doing something wrong. Yeah, give or take a parsec. Exactly. It launches it somewhere in the vicinity of Alpha Centauri, whatever. Just... But actually, that pretty much does it for Trebuchets. Look for an entirely new topic on Monday. We're probably going to get started with open rockets or some form of rocket design software, and we'll spend our time with that. We'll get familiar with it. We'll be able to design, Mach 10. We'll be able to design our own rockets and see how they perform in a very simple simulation. It's not going to be like like Kerbal Space Program or something like that, where you get to see it actually get launched up in the air and stuff like that. No, we're going to be looking at graphs and things, which I know, graphs. But at the same time, it's a very reliable modeling of how a rocket might fly if you changed a bunch of stuff on it, and maybe change the nose cone and increase the payload on it or whatever. Being able to see that stuff would give you a pretty good idea of how your rocket might fly in real life, mathematically speaking. So there is that, which is pretty useful. But that's probably what we're going to get started on Monday. So that should be interesting, hopefully. Otherwise, thanks for sticking it out to the end of Ancient Engineering. Hopefully you enjoyed it. Hopefully you got something out of it. But from here, we're going to move on to something entirely different next week. I don't have that material ready to go at the moment, but it will be ready to go on Monday. And in addition, I want to sort of keep things separated as far as material is concerned. So we'll get started on that on Monday. We'll get started on aerodynamics and rocketry and things like that. So that should hopefully be pretty exciting for you guys. And with that, we'll go ahead and we'll call it a class. It's been a pretty easy class today.